Hello, my name is Gianluigi Migliavacca. I coordinate the project FlexPlan, and I will introduce you to this special session dedicated to illustrate the outline of this project that is a very ambitious one and aims at putting some base for the grid planning of the future. So I will share my screen and introduce you to the presentations that you will see in this special session. So first of all, I will introduce motivations and goals of the FlexPlan project. Then it will be the turn of Hakan Ergun from Leuven, and he will introduce you with the FlexPlan innovative grid planning methodology. Then Raul Rodriguez from TECNALIA will speak about the FlexPlan intelligent preprocessor. Then Nuno Amaro from R&D Nester will introduce you with the FlexPlan regional cases that are 6 study cases till 2050 to study possibility of T&D grid upgrade needs, including flexibility. And then finally, Maxime Hanot from Inside will introduce the internal issues about the grid planning tool that is a big and challenging software engineering task. So I will start with some introduction on the motivations and goals of the FlexPlan project. So first of all, the high-speed development and deployment of renewables in Europe is making transmission and distribution planning more and more complex, and of course also affected by uncertainty due to the less variable behavior. Grid investments, which are capital intensive and have a life that typically spans several decades, could become critical in the sense that when a new line is commissioned, sometimes due to the rapidly changing scenarios, it could also be partially regarded as a stranded cost, so not be in any case so optimal as it was supposed to be when the investment was scheduled. Building new lines meets hostility from the public opinion, and that makes planning activities longer and affected by uncertainty. Variable flows from RES are generating a new type of very nervously changing congestion, intermittent congestion, that sometimes is better compensated by flexibility than with new grid investments, because new grid investments could turn out not to be economically justified. And there is, on top of that, an ongoing debate on the deployment of storage technologies and system flexibility to make RES grid injection more predictable, so the concept of virtual power plant. All that being summed up, our project FlexPlan, that has a starting date in 2019, so in October 2019, and will end up in September 22, aims at establishing a new grid planning methodology that considers the opportunity to introduce new storage and flexibility resources in transmission and distribution of electricity, and that as an alternative to building new grid elements. Our partnership is 13 partners coming from 8 European countries, and on top of research partners coordinated by RSC, my company, we have also 3 transmission system operators, Terna, REN, and ELES, respectively from Italy, from Portugal, and from Slovenia. And we have the distribution system operator concern, Enel, with in particular also a distribuzione that is the main Italian DSO. What are we doing in FlexPlan? First of all, we are elaborating a new planning methodology that creates in parallel a new tool for optimizing transmission and distribution grid planning. And that tool considers the placement of new flexibility elements in transmission and distribution networks as an alternative to traditional grid planning. Those flexible elements are in particular storage, demand response, and all kinds of storage, including also electrical vehicles and so on. Then, of course, in order to test the new methodology and the new tool, but also in order to perform real cases, realistic cases, we are developing 6 regional grid cases that encompass altogether most part of Europe. The map is the one that you see here on the left, that analyze scenarios at 20, 30, 40, and 50. And they are initialized in a coherent way by a pan-European grid model that is there in order to provide coherent border conditions for all 6 regional cases. Those cases are then analyzed, and the final stage of the project will consist in elaborating guidelines for the usage, in particular, of the national regulatory authorities, in order to suggest what potential role flexibility could have in the future, and what opportune regulation could be adopted in order to optimize its usage. A simple example to show our approach. We have here a small example with 5 buses, in which we have a big bottleneck between bus 4 and bus 5 that prevents the big generation set located in bus 5 to reach the big load that is located in bus 3. In order to cope with that, we have candidates that are 4 lines, that are the dashed ones, 2 storage systems that are the ones that are shown as batteries in green, and 1 flexibilization of the demand that is shown in green in node 3. The traditional solution of the problem is an expansion based only on new lines that is based on peak load conditions. But if peak load conditions occur only for a limited number of hours, that is not economically optimal. Another solution is, for instance, not to expand the corridor 4-5, but to flexibilize the load located in the bus at the bus 3. That is, of course, means to reduce and to adapt load to the possible provision of generation from RES, that of course has some peak generation in some moments and some low points in some other times. Then another possibility is, of course, should we have instead some wind parks at the bus 4 to activate storage in buses 2 and 5, and that could be very useful in order to cope with the variability at bus 4. So as you can see, there are many possibilities. We want to analyze all those candidates all together. And in order to do so, we are creating a new optimization model that optimizes as a whole the social welfare, and it takes as an input a lot of candidates of grid investments and flexibility options that are provided by a preprocessor. The preprocessor is also part of our package, and it will be illustrated by Raul in the next one of the next speeches. What are the most important characteristics of the new planning tool? So it implements a best planning strategy with a limited number of expansion options. We implement a mixed integer sequential OPF. We have a TND, so transmission and distribution integrated planning. We embed environmental analysis so that air quality, carbon footprint, and landscape constraints are inside the CBAs, inside the optimization model itself. We have a simultaneous long-term planning, including years 20, 30, 40, and 50, considered all together and not in sequence. We consider climate variance taken into account by means of a Monte Carlo process. We reduce the number of combinations by using clustering-based scenario reduction techniques. We incorporate all criteria into the CBA that is inside the optimization model, so inside the target function of the optimization. We implement probabilistic elements to replace n-1 security criterion, and we adopt ad hoc decomposition techniques to reduce calculation efforts. Regarding the Monte Carlo approach, we are implementing yearly climate variants that take into account different load and rest time series for different climate years, so wet instead of dry years, windy or not windy years. So of course the number of combinations are very high, and we reduce them by using clustering based scenario techniques. But if we adopted the Monte Carlo approach to solve the problem, which Monte Carlo run is separate, and so investment decision would be taken separately, and we would not know how to put them together. By contrast, we have to adopt a statistical model that takes into account all the different variables weighed with their probability. But in order to do so, we have a very heavy computational model. And so we resort to the Bender's decomposition that is able to separate the run of the master problem with investment decisions from separate and different dispatching models that implement different calculation for every Monte Carlo variant and for the different target years. For the definition of the candidates, as I said, we use a preprocessor. That preprocessor uses a non-expanded OPF for the different grid years in order to understand what are the needs for expansion of the network, and in order to calculate those candidates and see what expansion possibilities are there, it uses the Lagrange multipliers of the transit constraints in the optimization model that provide, of course, information in the sense of what could be the improvement of the target function in consequence of a unit relaxation of that constraint. And so depending on that, the preprocess elaborates the planning candidates. As far as the regional scenario generation is concerned, we use the three scenarios that are put forward by the T1DP document for 2020 by ENSO-E. So there are three storylines: national trends, distributed energy, and global ambition. That were used as such to set the scenarios for 2030 and 40. Then for 2050, a smart extrapolation of those scenarios was carried out, but also take into account the document A Clean Planet for All by the European Commission. As a whole, we have 9 scenarios that are 3 storylines multiplied by 3 grid years, 2030, 40, and 50. For the grid data, we adopt the T1DP transmission grid model for extra high voltage, but it doesn't provide any detail for subtransmission, where we use the OpenStreetMap and other consortium information in order to set detailed information on the networks. For distribution networks, we create synthetic networks on the basis of statistics on the real networks, because simulating real networks will be too demanding in terms of computational characteristics. I conclude with some preliminary regulatory considerations. Nowadays, grid planning problems are elaborated by TSOs and DSOs and sent to the national regulatory authorities for approval. But as in the new plans that we are envisaging, that also include storage and flexibility, TSOs and DSOs are not allowed to install and manage, normally at least, storage devices. A third actor that investors and aggregators, as a consequence, is appearing. And in order to take that into account, a triangle should be considered in which TSOs and DSOs elaborate planning proposals. Then they send them to national regulatory authorities, and when, in case they are approved, the national regulatory authority elaborate some incentivization for investors in order to realize this kind of plans. Alternative would be that national regulatory authorities charge system operator to set up calls for bids for investing in promising nodes, or in some special cases, it would also be possible for TSOs and DSOs to manage, if in a non-profit oriented way, some storage devices. What matters at the end is that the real-time market dealing with grid congestion should reflect the real situations, and so nodal market would be necessary for that. They should provide optimal locational signals in order to orient aggregators bidding in the network, and define products that don't create entry barriers and don't discriminate flexibility provider, in particular storage actors. So I want to remember you as a source of important information the website of the project FlexPlan, and in particular we have recently published for energies a 30 pages long paper that I recommend you to read in order to have more details on that. So for the moment, I quit with my general presentation, and I give the word to Hakan Ergun, who will present details on the planning tool. Please, Hakan.
Thank you very much, Gianluigi, for the introduction. Yeah, as Gianluigi said, I want to introduce you to the planning model that we have been developing within the FlexPlan project. But before diving into the details of the planning model, I first want to set the scene and talk about network planning in general. So eventually the transmission or the distribution network is the physical place where a number of actors come together to exchange electricity and to exchange energy. And of course, all these different actors, they have their own objectives and they come all with their own uncertainties. And then eventually the job of the grid planner is to figure out for the future where to make the best investments, considering all the objectives of the actors, but also all the uncertainties imposed by them. But in general, the job of the network planner is to find the 4 W's of system planning, what I like to call. So first of all, where to invest, which means which particular connections should be built or extended in the network, what type of investments do we need, so which technology am I going to choose, am I going to trade off between different technologies, am I going to invest in AC or DC technologies, overhead or underground transmission or distribution, or introduce FACTS devices and so on. Of course, a very important aspect is the temporal aspect of when to invest, as such large investments don't happen over time, and the network planner has to find the best possible sequence for the network investments to have a robust expansion plan. And at the end of the day, as Gianluigi was just talking about, it's also very important to have the right incentives for investments. So the question becomes eventually who pays for it, how are the investment costs and the revenues allocated. So what are now the main challenges when you want to come up with a network expansion plan? Well, first of all, how do you deal with uncertainty imposed by the renewables? And it's not only the uncertainty that comes from the intermittency, it's also the uncertainty towards the amount of renewables that are going to be in the system in the coming 10, 20, 30 years. Second, how to model the environmental impact, because this is getting a more and more of an issue, and when you're building now large infrastructure projects, you have to be very careful of how to do this. Thirdly, only looking at transmission systems or distribution systems will not give you the most perfect picture, so you have to do a holistic system design of both systems together in order to avoid inefficiencies in the planning. And last but not least, of course, not only looking at traditional system investments extending lines, but it's also very important to account actually for other sources of flexibility, meaning demand flexibility and storage as a trade-off with respect to the classical line investments. And of course, trying to put all these things into a single optimization problem is then very challenging. So how did we now try to tackle this challenge within the FlexPlan project? So we came up with an optimization model, which is outlined here on this slide. we are actually using three main types of inputs. First of all, the candidate transmission lines and cables that we could have in the planning problem, HVDC connections, possible phase shifters, storage and demand flexibility, which will be provided by a preprocessor tool also being explained in the next presentation. As input data, we have generation and demand time series for the three respective planning years that we are looking at. And then eventually we have, of course, the existing transmission and distribution network coming from the TYNDP dataset, but also a number of other data sources, which will be explained later. And in a very first pre-processing step, we are quantifying the landscape impact cost and the carbon footprint costs, and then putting these things into an optimization model where our objective is to maximize the social welfare or minimize the costs of operation and investments. And our decision variables are, of course, the investment decision variables, which are binary in nature, but of course also the hourly dispatch of generators, demand flexibility, and also storage. And of course, we have to account for the network constraints, for security constraints, and the characteristics of demand flexibility and storage. So this is how our objective function looks like. And we have formulated the social welfare objective as a cost minimization problem, as it's sometimes not very easy to quantify potential benefits coming from storage or demand flexibility without doing a detailed market simulation. And as mentioned, for each planning year and for each hour that we are considering, we are accounting for the operational cost of existing equipment, of candidate equipment. We are also accounting for the expected cost due to the outages that might be caused, and then, of course, also the capital investment costs for the candidate equipment. And we try to internalize the environmental impact cost as part of the objective function, which I'm going to talk about in a bit. How did we model the network? For the transmission system, we used the linearized DC power flow equations to represent both the AC and the DC network in order to keep the problem tractable. For the radial medium voltage distribution networks, we have chosen for the linearized dist flow model, which allows us to also account for the voltage magnitudes and reactive power, which is very important still because of the Rx ratio of the medium voltage network. Of course, also modeling all the low voltage networks would be out of scope of such a planning exercise. We have also used separate investment decisions for AC lines, DC lines, converters, and PSTs. This way, actually, we can choose to invest into point-to-point or meshed DC networks, for instance. And last but not least, also the network model allows the possibility for accounting for line replacements as well, meaning that a new line at a particular corridor might only be built if the old one is decommissioned. And for the details of the network modeling, I will refer to the project deliverable that we have available on the website. We have also developed a parameterized generic flexible demand model in order to account for the characteristics of the flexibility. And this flexible demand model is a superposition of actually three components. The very first component is the voluntary demand reduction with respect to a reference demand, which we have depicted here in red. Of course, therefore, we need to have certain constraints in terms of power and energy, because of course, no user is going to just decrease his demand to zero for no reason. So it will be only possible in a small range and also only for a certain amount of energy. Of course, in hours where there might be adequacy issues, some involuntary demand reduction might occur. But of course, then this involuntary demand reduction will be penalized with a very large cost, usually 2 orders of magnitude higher than generation costs. So to be used just as a last resort. And then last but not least, of course, we can do demand shifting, where at the end of the day, the energy consumed will remain the same. But of course, we need to account intertemporal constraints for this because we cannot shift demand infinitely in time. How did we model the environmental impact? We have there 3 main components. The first model is the air quality impact model. And there we developed a linearized model starting or using reference historical data about the emissions of power plants and then the concentration of these emissions in the air. And starting from there, we can then also look at the health impact of these emissions and try to monetize this. And this gives us the possibility to represent the air quality impact cost of a conventional generator with respect to the megawatt hours produced. And this we can then just internalize in our objective function. Secondly, we have modeled the carbon footprint of the new assets that we are investing in by means of a life cycle analysis, which then take into account how much CO2 has been emitted in the production of this equipment, but also, of course, during the installation. And last but not least, we are modeling the landscape impact by using geographical data in combination with an optimal routing algorithm. The geographical data includes the different installation areas between two possible substations, like it is depicted here in this picture, which can be nature protected areas, urban areas, infrastructure areas. And of course, we can then assign different weights depending on the landscape impact to these areas, and then try to find the best transmission route along this corridor, and then decide where to invest into overhead lines and where to invest into underground cables, while internally taking into account the landscape impact. As I was mentioning before, we try to have a holistic system view and really to look at the system design, both of the transmission and the distribution system. So the model that we came up with is very generic and supports the modeling of transmission systems only, the modeling of distribution systems only, but also the combined model of both. But of course, in the realistic test cases, as we are envisioning to apply it, where we have potentially hundreds and thousands of buses of transmission, it is, and if you imagine that you also have several distribution feeders connected to all these transmission nodes, then the system is going to be huge. So we had to come up with a model decomposition in order to have a tractable optimization model. And therefore, actually, we are first solving the distribution system planning problem for a number of flexibility objectives, which means in the very first case, for instance, we can say that the distribution system becomes inflexible with respect to the transmission system and only tries to minimize the investments in the distribution system to solve local congestion. But then increasingly, we can solve the same problem with the objective of providing more and more flexibility towards the transmission system. And this allows us to make a decoupling for the transmission problem, where we can then just plug the flexibility levels of the distribution system as a planning candidate into our model with associated investment costs. And as Gianluigi was already also mentioning in the introduction, our problem is quite heavy in terms of optimization. So we have also developed a Bender's decomposition approach, where we are first solving the binary investment problem without network constraints to obtain a lower bound of our objective, and then implementing the outcome of that problem into the operational problem, which then only becomes a linear problem in a continuous variable space. We can actually determine the operational cost and then plug this in as an upper bound to our objective function. And then by successively solving this problem, we can actually come towards the global optimum and solve our problem in a more tractable way. We have also implemented this model for validating and testing our model, which then serves also as a test bed for the actual planning tool, which will be which is being developed, where Maxime is going to talk about later. I refer to the two publications which are here for the details of the implementation as well. What can we do with this proof of concept implementation? First of all, we can look at in a detailed way to the sensitivities of the model. Here I just picked a very simple test case that we are using on the basis of Italy, a 6-bus network, where we have then looked at what would the optimal system expansion be if we wouldn't have any demand flexibility versus the case where we have demand flexibility. And this we have done for a number of climatic variations, which is here indicated by the cluster number. And of course, not surprisingly, we see that the total system cost consisting of investment and operational costs, of course, becomes much higher in demand flexibility, in the case where we don't have demand flexibility, because we end up installing storage facilities which are only utilized for a small number of hours in a particular year. The implementation that we have also allows us to test actually the sensitivities with respect to the probability of certain scenarios occurring. So here on the left-hand side, we have done an analysis where we have analyzed the probability of a high renewable energy scenario occurring, and then we can see how the total system costs are changing with respect to the likeliness of higher renewable generation being existent in the system. And as our optimization problem has many dimensions and it's a very complex problem to solve, we have also been looking into different scenario clustering methods and time series clustering methods. So also this proof of concept implementation helps you to analyze what the quality of your clustering methods are. But I'm not going to go into further detail there. More details you can find in the respective deliverables. And this brings me to my conclusions. So within FlexPlan, we have developed a comprehensive planning model to really find the trade-offs between flexibility and classic grid investments. And we can apply this methodology to both transmission systems or distribution systems or both combined. To keep the problem tractable, we have come up with a number of decomposition techniques, and we have also implemented this in a proof of concept software library, which we will open source in the course of the project. So I thank you very much for your attention, and I'm looking forward to your questions after the presentations. Thank you.
Thank you, Hakan. Then we pass to the second speaker, who is Raul Rodriguez from TECNALIA. He will speak about the preprocessor and the smart ideas that lay at the ground of this, which could be said to be an artificial intelligence implementation tool. Please, Raul.
Okay, thank you, Gianluigi. Yes, in this presentation, I'm going to introduce you the main aspects related to this preprocessor that we call in the projects, in the FlexPlan project, which main aim is to select some candidates for the planning tool to decide among them which are the best grid extension options. So I will speak first of the work that we have been doing for let's say preparatory work to this software development. Afterward, I will speak about the methodology and the main steps of it, which are the main things that the preprocessor is performing. Then very briefly, some comment about the integration with the planning tool and how that fits into the global planning process of FlexPlan, and the way or the point in which we are now in this at this time of project development, and where to find the reference documents where you can find more information about what we are doing around this topic. So first,
maybe you can share the presentation. Sorry, Raul.
Oh, sorry. Yeah, I thought it was heard. Okay, now you can see it. Yeah. Okay, then. First, the first task that we did was a bit of literature analysis, taking into account which were the services that flexibility elements could provide to the network, especially focusing on storage and demand response. And among all those services, we selected the congestion problem because this is the most important problem for the planning process. So here we focused on the operational strategies and ways to find the best location for flexible resources in order to solve these congestions. This is all this analysis of services and operational strategies of flexibility elements is summarized or put into a deliverable that is accessible in the FlexPlan web site. And then a second input job was done on the to search about the characteristics of flexible technologies, so we could then input this information into the preprocessor tool and be able to perform the analysis we wanted to do. So here we search for some technologies that can provide flexibility to the system, mainly storage and flexible loads, and checked for them some of their main parameters and characteristics related, for example, to flexibility capability, technology maturity, cost, and environmental impact. In this second work, we also perform a task around the modeling of flexibility resources, mainly focusing on storage and flexible loads again. So these two works can be found in two deliverables that can be found at the project website, and I will provide more information about that at the end of the presentation. Going into the detail of the methodology, we can say that this is a tool that is supporting the planning process. So this is a tool that its main aim is to provide a set of candidates to the planning process with the objective of reducing this computational effort that we are needed to optimize, let's say, to solve this optimization problem that was before mentioned by Hakan. So the idea would be to limit the set of candidates that the planning problem is dealing with. So for this, we need to interact with the planning tool according to the methodology or general methodology already explained also by Gianluigi in its presentation. So main steps of the preprocessor are to analyze which are the congestions that we can find in a non-expanded grid model. So taking the grid as it is for a certain year, we are here dealing with the timeframes between 2030 and 2050. So the idea would be to take this grid as it is the first year, for example, 2030, propose some candidates after recognizing which are where is the problem or the congestion problems that they may appear in the network. So be able to say where those congestions will be, and for those specific locations, try to through a check of constraints and characteristics of the congestions, be able to provide a set of candidates that will then be passed to the planning tool for it to decide among them which are the best solutions for grid expansion. And this is done, as Gianluigi mentioned, not only for 1 year, but for a time frame that goes from 2030 to 2050. So this is done in a loop in 3 consecutive steps, where once we have analyzed the first year, 2030, then we get the non-expanded grid for 2040. We perform also, we run the preprocessor and provide a set of candidates. Then we do the same process in the end for the non-expanded 2050 network. And once we have candidates for all 3 periods, let's say for 2030, 2040, and 2050, the planning tool would make optimization, a complete optimization of that, and would say which are the best candidates to invest upon and for grid extension in the whole period, taking into account all the considerations that have been mentioned in the previous presentations. So going a bit into the detail of the preprocessor methodology steps, so we could get the optimal power flow results from the planning tool suite. Here we will use Lagrange multipliers, locational marginal prices, and power transfer distribution factors mainly, but also power flow directions. And also here we need to consider that this information will come not only for one case, but here we need to consider that we will have variants, scenario variants linked to this that Gianluigi said before about climate differences between years and all that. So we need to take all this information, and from here what we will do is analysis of congestions, considering which are the values of Lagrange multipliers, statistical values, but not only the numbers, but also the occurrence of, I mean, not only how big the congestion is, let's could say for brands, but also how many times in a year this happens and in how many scenarios this happens. So we will take that into account to make a ranking of which are the network branches that really suffer or are expected to suffer more congestions. We will check the characteristic of these congestions also, if how many congestions we have in a year, for example, but also if these congestions are consecutive or not in the hours of day, for example, because that make us or restricts, let's say, the type of storage or that of technology that we could use to solve that congestion. So once we have characterized the congestions in the system, we do a check of for that specific point in the network, which type of bus we have there, which availability of some resources we have there, for example, water or caverns, in order to propose some or other technologies, which type of loads are supplied in order to know if we have any flexibility availability. Also, where this bus is located in an urban or rural area, in order to know if we can propose technology that, for example, is of low density, let's say, or of high density. Also the same about the geographic characteristics of the place, if it's a mountainous area or not, or in general also if we have any type of restriction related to that area, so that prevent us to propose a type of technology or a building or whatever that it's not allowed there. So once we have checked these locational restrictions and congestion characteristics, then the last step would be to propose a set of candidates to the planning tool. And here we are considering some storage technologies, different batteries technologies, lithium-ion, sodium sulfur, and flow batteries. Also hydrogen, pump hydro solutions or plants, and both compressed air storage and liquid air storage systems. Related to demand demand response, we are also considering the possibility to make these loads in the system flexible, or to be able to make them flexible and to provide flexibility to the system. And we are considering these new, let's say, approaches of grid extension or expansion together with conventional or more conventional systems like lines and cables and transformers, so that we can compare among them which is the best solution. This is something that will be done by the planning tool, of course. Last, we are considering also phase shifting transformers as an asset to provide flexibility to the system. So very briefly, the integration of this methodology with the planning tool, I mean, this could be something that is clear, transparent for the user, because the user could only communicate with the planning tool. So this part of the preprocessor would be in the back and would be, as said, transparent for the user of the tool. What we are doing now, I mean, the methodology is almost finished, or is finished at this stage, but of course this then after validation some adaptations may be needed. So we are now closing the last open points. We are performing now the integration between the preprocessor and the planning tool, and we already started to validate the software in both in a standalone way, with, let's say, before connecting it to integrating it with the planning tool, and now that it's been integrated, also we have already started with this validation of the tool. And this, of course, will go on until we get the final version. So we need to test these regional cases that will be explained afterwards by Nuno in one of the next presentations. As mentioned, you can find the reference documents at the FlexPlan project website. We have at the moment 3 of them. The 2 that I explained at the beginning that are introductory on the services characterization and on the flexibility element characterization. And you have a 3rd document that speaks about the methodology of the preprocessor tool that I just explained, that it's not totally finished, let's say, because, as I said, the validation may change and produce some small adaptations, but it's nearly finished. So with this, I thank you, and I also wait for your questions after the presentations.
Thank you very much, Raul. It was a comprehensive presentation of the preprocessor. Now we pass to the next presentation by Nuno Amaro, R&D Nester, who will speak about the scenarios and the regional case studies that we are performing in SmartNet. Thank you. Maybe the microphone is Please put on the microphone.
Yes, sorry, there was an issue with that. Okay, so good morning, everyone, and thank you for your presentation, Gianluigi. So for this part of our special session, I will just quickly present the regional cases we have in FlexPlan, and how they will be able to validate the solutions we are developing, and then also to contribute to the outcomes of the project. I will quickly explain what are these regional cases and what are the 3 different, what can be called building blocks for them. So the grid models, the scenarios that we are using, and all the characterization data for load and generation. And then a quick explanation of what is the envisaged workflow for these regional cases simulations. So as we saw in the previous presentations, the main goal of FlexPlan is to develop an innovative grid planning tool, and how we are validating this tool within the project scope, it's by using 6 ambitious regional cases that cover almost all Europe, as you can see in the map. And the outcomes, the main goal is that the outcomes of these simulations provide realistic network planning plans, and allow also to evaluate flexibility sources in these grid planning studies. Each regional case is composed of 3 different main blocks. So the network models, which includes full transmission and distribution systems, the energy scenarios to be simulated for long-term plan analysis, so up to 2050, and the full characterization of generation and flexible load elements. For the grid models, so we all know that the existence of accurate grid models is core for the soundness of solutions in simulation projects and other works. So in this purpose, in FlexPlan, we set up a complex activity to develop realistic grid models, which cover almost all Europe, and they include both transmission and distribution systems. For the transmission systems, we are using a pan-European real transmission network model. I mean, real. It was provided by the TSOs. And for the distributions networks, so we are using synthetic network models, which are also based on statistics from real networks. And it is important to highlight that these models are large scale and realistic ones. So we have a one-to-one representation of grid nodes when we compare our models to the models that the TSOs also use in their own expansion plans. So for the transmission system, we are our main data source. It's a real model of the pan-European transmission system from ENTSO-E, which uses real transmission models provided by the TSOs. There is, however, some details. So in some countries, the sub-transmission, what can be named the sub-transmission network, are missing. So in these cases, we had to complement this data received from ENTSO-E with either TSO level data or recurring to other open sources. And the models were fully validated by us and complemented. So as one example, we included the full description of the geographic location of all substations in these models. So that you can have more or less an example on this activity, you can see here the transmission model we are using for France. In blue, you can see the blue lines, it's the ones that were included into the ENTSO-E received dataset, and the green ones are the ones we are adding on top of that with our own complementary activities for the creation of this model. Then for the distribution systems, so these are based on synthetic networks, as it is very, very hard or almost impossible to obtain realistic models for all Europe. And these were created using a dedicated methodology, which is based on statistics from real networks. Not only are they real, they are also representative of the different countries or the regional cases. And inside each country, they are also representative of the different geographical conditions. So, one example, we consider different networks for urban or rural areas, which allow us to have a realistic approach also on the simulation of the distribution systems. In terms of the second building block, so the scenarios that we want to simulate, in the scope of FlexPlan, we create 3 different scenarios to be simulated for the 3 target years, so 2030, 2040, and 2050. Each scenario considers 5 variants, which results from a clustering algorithm of 40 different variants corresponding each one to a different climate year. And let's say the 3 macro scenarios are based on the TYNDP 2020 storylines from ENTSO-E. We kept the same names for purpose, for simplification. So we have the national trend scenario, the global ambition one, and the distributed energy scenario. And of course, the 3 of them presents different forecasts for the pan-European system in the next 3 decades. And these 3 scenarios were further adapted by us in the FlexPlan scope to include 2050 data, because in TYNDP there was no data for 2050 at country level. So we made for that an extrapolation of data from TYNDP 2020, so data from 2030 and 2040 existing already in this data set, and we validated our own extrapolation using the A Clean Planet for All Energy Package program from the European Commission. Now, the TYNDP 2020 scenarios provide data at national level. So what we have as one example, it's the installed capacities per technology at national level and the national load profile, so the aggregated load profiles. Due to this, we had to set up as well a dedicated methodology that allow us to convert these into the nodal level time series data that we need to simulate the scenarios. So this is composed of as well of 3 different steps. So on the first step, we had a regionalization of the capacities for generation, for renewable generation and loads. So the national level installed capacities were disaggregated at regional or local level using a multi-criteria approach. So as one example for loads, for the disaggregation of load, we have a direct correlation with urban density. And after this regionalization, we created the adequate time series for both load and generation at regional level. Then we run a market simulation at pan-European level to obtain coherent cross-border exchange between the different countries, or in our case, more important, between the different regional cases. And finally, on the third step, we run a further adaptation in order to have a nodal allocation of generation and time series. So starting from the regional levels we further disaggregate these into nodal level for load and generation to have the time series to be simulated. And we go up to the level of having both load and generation into the distribution systems nodes. So we have a full nodal time series approach. Then the third one and final major building block of our regional cases, it's the characterization of load and generation data. So in order to realistically represent the technical conditions we have for not only for the current but also for the forecasted pan-European system, and of course to fully demonstrate the capabilities of our tool, we had to take these additional steps for load. So as I said, for load, they major include the identification of main load centers, so which can act as flexibility providers, so for demand side flexibility. And this characterization includes the definition of their exact geographical location and also other technical parameters that allow us to characterize their flexibility provision. On the generation side, we identified different plant-specific details, such as the installed capacities, their pollutant emissions data, their geographical location, and the fuel type, and so on. I want to highlight that this is done at plant level, and of course, it allows us not only to see the exact location of power plants, as we can see on this example for Italy, for the installed hydro capacities, but it also allows us to run the environmental impact assessment studies, as we saw before in Hakan's presentation, since we have the pollutant emissions data in a plant specific analysis. So these three building blocks allow us then to start up our workflow for the regional cases simulation, which is currently starting. So at this stage, so we already had this exhaustive and extensive data collection activity and data validation, so all pre-processing stages. So we have our grid models and we have the different scenarios which are now ready to be simulated. So we have 3 scenarios. As you remember, we also have 3 target years, and for each one we will use 5 different variants, so a set of 5 different variants. Then the next step, which is now starting, it's actually to run the OPF calculations on the planning tool. So we will start with an OPF calculation for the first 2030 non-expanded network scenarios. It's important to highlight that we are talking about a full year, so for 708,000 and 60 hours OPF for 5 variants. And then we enter a loop between the planning tool and the preprocessor that we saw before in Raul's presentation for the selection of the different expansion candidates for the different scenarios and the different target years we have. And then, of course, the main outcomes of these presentations will be the different network planning procedures, the expansion candidates, let's say the expansion plan, which considers both flexibility solutions and also the traditional grid reinforcement, so the creation of possible new lines and installation of new transformers as one example. And this is it from my side. So with a quick explanation on what are our regional cases and what we will do on this simulation. So thank you very much for your attention.
Thank you very much, Nuno. I think that this presentation gave you the impression of the complexity of this generation of 6 regional cases. And so that gives also the measurement of how big and how robust should the planning tool be in order to be able to withstand so big and harsh proof. And so Maxime will be the last speaker to tell you about the realization as a big and challenging software engineering task of such a big grid planning tool. Please, Maxime.
Thank you, Gianluigi. So indeed, my presentation, which will be the last for today, is going to be about the implementation of the planning tool itself, which is indeed a challenging software engineering task. So my presentation will be in 3 parts. First, I will describe more the topic of the architecture of the planning tool, the design, the interactions with the different parts. Then we will speak about the implementation itself and in particular the challenges that we are facing. And finally, I will showcase a bit the graphical user interface and at least the mock-up of the graphical user interface because it is still under implementation. So let's start with the architecture and the design. And as it was already explained by my colleagues in the previous presentations, the planning tool, it aims at solving a very large-scale optimization problem. I won't go again into the modeling, which was presented by Hakan, but we have as input some time series, some grid data, some candidates, and we model this as a mixed integer linear programming model with an objective function, with some decision variables, with some constraints, and we want to find what is the optimal investment decisions to upgrade the grid, which can be either like classical reinforcement of the grid with new lines, but also storage access and demand flexibility. And the planning tool that we are developing, it's written with the well-known Python language, and we are solving the optimization problem with IBM Cplex, which is one of the leading mathematical programming solver. And the tool is made available through the AWS web server so that users can access it either through the API or through the graphical user interface. But how does it work? What are the interactions within the planning tool? And in particular, the interactions with the preprocessor tool, which makes the tool quite complex. So first, in terms of input for the planning tool, as I was saying, there are 2 main inputs. First, the grid model. So it's everything about the topology of the power system, the different buses, lines, and so on, and their technical characteristics, which is similar to the equipment profile files from CGMS. And in the future, right now, we have our own custom input files, but we could imagine also to support CGMS files in the future. The second type of data input is the future scenarios for 2030, 2040, 2050, with all the data which is time dependent. So basically load and generation profiles, as well as some storage devices data. And it's so similar to the steady state hypothesis data files from CGMS. So with these 2 data, the planning tool is first computing the non-expanded optimal power flow. And the goal of it is really to identify what are the bottlenecks in the grid, what are the lines which are congested. And it gives the results of the OPF to the preprocessor as locational marginal prices at the buses, and as well as power flows and Lagrange multipliers associated with the branches. With that information, the preprocessor is then able to define what are the candidates for expansion of the grid. The candidates, which can be, as I was saying, new lines, which can be demand flexibility or storage assets. And the preprocessor is then giving to the planning tool the location of the candidate, the size, and the cost. And with these new candidates, then the planning tool is performing another optimization problem, which is the grid expansion planning problem, to determine what are the optimal investment to be done to minimize the system global costs. So that's the interactions between the planning tool and the preprocessor. And that's really the main role of the FlexPlan tool we are developing. Of course, as it was said in the previous presentation, it's not all. Another part of it is also to be able to perform the scenario reduction methodology, so that you are able to move from k different variants to a reduced number of variants for each node to handle the complexity of the problem. And for that, we use the well-known k-means algorithm, clustering algorithm from the scikit-learn Python package. And the methodology is not only able to reduce the number of variants, but also to go from yearly time series to monthly, weekly, or daily time series. And the way it works, it's based on scenario feature that we extract from the scenario data to perform the clustering. One last thing about the architecture and the design, it's about security. Because we are dealing with some sensitive input data, we are dealing with grid data, and so security is really an important topic for the planning tool. And we implemented several security measures for the planning tool then. First one is about how we handle the input. So we are only keeping the input during the processing of the data, and it's not persisted afterwards. Only the output is persisted. Then we use IP whitelisting to limit and control the access to the planning tool. We also use authentication to know who is accessing the planning tool and verify its identity. And finally, for the transfer of the data, we use the well-known HTTPS protocol to have a secure communication. So that was more about the architecture and design, and now about the implementation itself. The way we are developing the planning tool is really in an iterative way, in an agile way. Indeed, as it's really a quite complex software engineering work, it's important to go step by step and not to try to create everything from the beginning. So it's why we started only with a simple connection prototype to make sure that the interfaces between the external world and the planning tool were working. And from this connection prototype, we expanded it step by step towards the final planning tool. So with first being able to run a non-expanded optimal power flow, then implementing the scenario reduction process, expanding the OPF also to the grid expansion planning when we have candidates. Right now we are at the step of the integration of the preprocessor, which is the step 5. And at the end, we are also at this step a bit in parallel, the implementation of some decomposition methods to be sure to be able to solve the problem in a tractable time. I will come back to it a bit later. Another point which is very important is about testing, because it's quite a complex work, and so we need to ensure that it's working as expected, and so testing is really a fundamental. And in the context of the FlexPlan project, we really had the chance to have on one side the FlexPlan.gl package, which is based on the open source package from Julia, that we were able to use to compare with the FlexPlan planning tool on a small case model. Of course, the FlexPlan.gl package is only there to make some tests, but still, we are then able to compare with the planning tool on some small case tests. Then two implementation challenges I would like also to share with you, and that we face and are still facing in the project. The first one, it was about data transfer. We have quite a lot of data to be shared with all the time series, all the grid data, and so it was important to minimize the time of the transfer. The transfer. So it's why we decided to use the JSON format, which is a very light and fast to read and write format. And also the content of the input file were really optimized in order to minimize the size of the input file. And furthermore, we also implemented the handling of gzip compression and decompression to also reduce the time to transfer the data. So this for transfer, but then of course, the other main challenge is of course the computation, and this is true for two aspects, for the memory and for the time, because optimization problem, they require a lot of memory to be solved. So it was also important to us to implement some measures to reduce the memory need. And on this side, what we are currently implementing is to decompose the full year problem, which is really memory demanding, in some sub-problems which can be run month by month. So this is more for the memory. And then on the other side, we are also trying to improve the time efficiency with tuning of simplex parameters. It's important to use directly the most suitable available algorithm for our problem. And also by implementing some decomposition methods, as it was a bit explained by Hakan, like the Bender's decomposition, to solve the problem more efficiently. So this was about the implementation challenges. And then to end this presentation, I would also like to showcase the future graphical user interface, which will be available to the user to interact with the backend, with the planning tool. So this graphical user interface, it is still under implementation, which means that what I'm going to show you is for now only the mockups, but it's really how it will look like, just that the data shown is like dummy data. And the first part, which is very important, is the simulation dashboard. It's really the cockpit from where the user can create new simulations and have a view on all the simulations already performed. So here you really have the list of all your simulations, and you can from there quickly access a panel with summarized information of the different runs. So for example, the cost summary with what are the operational costs before investment and after investment if you follow the recommendations of the planning tool, and what are also your investment costs if you want to follow the recommendation of the planning tool. There are other, of course, information. For example, what are the candidates to be invested in? And then we also have a visualization tool, which goal is really to be able to visualize the different steps of the FlexPlan planning methodology. So the first step is simply to be able to visualize your data, your grid as it is today, with the different lines, buses, PSTs, and so on. This is really what is the current state. Then you can visualize the results of the preprocessor. I was explaining the preprocessor no, not the preprocessor, sorry, not yet, of the OPF. The OPF, which goal is to identify what are the congestion in the grid, what are the bottlenecks with the congested lines, then with buses with high Lagrange locational marginal prices. And then afterwards, you can see what are the candidates which are provided by the preprocessor. So what are the candidates lines, but also what are the buses with some storage candidates or flexible load candidates. And the last step, when the planning tool is performing the optimization, it's to see from all these candidates, what are the remaining ones which were selected. So the ones which are no more there are the ones which were not selected, and the ones which still appear are the ones which were selected. So that's it for my presentation. Thank you very much. And I think I will give back the final words to Gianluigi then.
Thank you, Maxime. That is the final presentation of this special session. Now it's time for you to get interesting questions, and we will be very glad to solve them and to provide the clarifications on our project. That it is, as you can have seen from our presentation, an ambitious one that aims at creating the basis for the grid planning of the future. Thank you very much.